Hi, hello, I'm Matthew McGovern. I teach physics in the Hawke's Bay, and this is another video in the NZIP series on energy, how to teach energy. So this is looking at a diagrammatic method called energy bar charts that you can use in your classroom for junior kids or senior kids. That ends up being really helpful in assisting them to understand the concepts behind conservation of energy. So I'm going to do this in two parts. Today, this first video is just why do we use energy bar charts and how can we use them? And then I'll follow up with another short video on a list of different examples that you can just take and use in your classroom. So why would we want to use energy bar charts? As explained in the previous videos with Gary and David, energy conservation, it's an abstract idea and it can be difficult for students to understand. And the way we're traditionally taught it is using calculations. The issue with that is you've got two different things you're trying to teach. You're trying to teach the energy conservation concept, and you're also teaching your students to be good with calculations. And in practicing the energy conservation concept using calculations, their cognitive abilities can get overloaded. And although they might get calculations that look correct, they might come out of the exercise and not have learned anything about the energy conservation concept. And we have an overemphasis on just labeling forms of energy for the sake of labeling it. The whole point of energy as a concept is to be used in conservation of energy. The total energy in the system before and afterwards is the same. That's what it's useful for, as opposed to just labeling things for the sake of labeling them. So, why would we use energy bar charts? Okay, just like why would we use a map? When you think about driving and you think about using a map looks nothing at all like the route that you would take, what you would actually see out of your eyes, right? It's a complete abstraction. The diagram itself is something that we've created as humans to represent where we're going, and it actually turns out it's a very helpful way of imagining where we're going. Energy bar charts are the same. Okay, so they're a representation and they help us to visually see what's going on, just like a map helps us to visually see where we're going. Energy bar charts aren't the only type of diagrammatic representation of energy and energy conservation. The other type is Sankey diagrams. So you've probably seen Sankey diagrams before where you see an arrow and it's split off into the different types of energy. Energy bar charts are used around the world. They're used in a couple of physics programs that are based on best practice and research. So you can certainly look up different examples and different questions to use with your students. Okay, so they're not something that I've invented. They're something that I've just taken in all the reading that I've done around how to teach energy. Alright, so how do you go about using energy bar charts and teaching to your students? So there's 4 steps, and we're going to go through each of these steps. Choosing a system, which is something you probably overlook as teachers, certainly in a high school setting. Identifying the initial and final states, which seems really obvious to us teachers, but for students, there's a lot of evidence in the research that they actually struggle with this. Assigning energy amounts, and then we use our bar chart to generate a mathematical expression. Okay, so let's say we've got an example here of Tiger Woods dropping a golf ball from head height. What energy does it have just before it hits the ground? So we'll go through all of these things. The first thing was to choose a system. So the system in this case I'm going to choose is the ball and the earth. I'm not going to choose Tiger as part of the system. We always choose the earth as part of the system because gravitational potential energy never resides in a single object. Okay, so the gravitational potential energy is never in the ball when it's held up high. Gravitational potential energy requires 2 things. And so it actually resides in the field between the ball and the earth. So we're always picking earth as part of our system and then whatever object we care about. So that is the definition of what system choice is. It's the objects we care about, and the main one we care about is the ball. Because we're describing gravitational potential energy as well, we need to also put in the earth. Okay, the initial state I've said is up high, where Tigers let go of the ball. What I now do is assign the energy value to that. So when it was up high, it wasn't moving. So it's the instant it was let go. So it has no kinetic energy and it has some gravitational potential energy. Now I can assign any amount to it as long as I'm consistent within my problem that I'm going to work out. So in this case, I've decided to assign 5 bars of energy. And this is something when you go through these problems with your students, you can talk about why did you choose to assign this much energy to this and this much energy to that. So it can actually induce some quite interesting discussions. From that, I'm now going to look at the final state. So in this case, I'm going to think about it just before it hit the ground. This is an example of a question, an issue that students have, and a lot of them will say, well, the final state's when it's resting on the ground, it has no kinetic energy, it's not moving at all. And so as physicists, it seems obvious to us that we're trying to think about it the instant before it hits the ground. So this is a practice that's good for students to get into, is being able to define the initial and the final states and then have discussions about that as well. So just before it hits the ground, I'm going to say it has zero gravitational energy, it's at ground level, but it's moving. So it has to have some kinetic energy. And this is the conservation of energy here, is that the amount of energy that I started with, 5 bars, has to be the amount of energy that I finish with. Okay, energy is conserved. I've got 5 bars here, I've got 5 bars there. And then I can write an equation. I can turn this visual representation into a mathematical representation. 5 bars of gravitational energy become 5 bars of kinetic energy, and so we write that as gravitational energy is equal to the kinetic energy. And then if we wanted to do calculations, we could then go on and do the calculations. Even for my year 12 students, I go through this process and get to forming an equation without any calculations for a couple of lessons. So we just practice going through this process again and again for different situations. And then finally, once we've all nailed that, then we can go on and add some calculations in there at the end. There are some nuances. So one of the nuances is that when you have energy flowing into or out of a system, this is the idea of work or heat. And this is where this idea of a system comes in. So let's say we've got Dustin Johnson here, who's hitting a golf ball, and I want to look at my initial state with the golf ball on the ground, and then my final state when the golf ball is up high, at its highest point, but it's still moving. So again, I want my system to be the ball and the earth. My position A is when the ball's on the ground, it doesn't have any energy. And then my position B, it's up high, so I've given it some gravitational energy, and it's still moving, I've given it kinetic energy. And so then we look and we say, well, hang on, I had no energy to start with, and it had 5 energies at the end. Seems like conservation of energy is broken. I thought energy before equals energy afterwards. And this is the power of defining a system. Okay, so the club is where the energy came from for this ball, and the club is outside the system. It's in the environment. So how do we transfer energy from outside the system into the system? We just do it little arrow. I've got 5 bars coming in here. 1, 2, 3, 4, 5 bars of energy become my 5 bars of gravitational and kinetic energy combined. This is your definition of work. This is such a better definition than just something as a sentence. Kids can actually see what work is. It's the transfer of mechanical energy into a system, and you can have the transfer of energy out of the system as well. You can have those arrows pointing out. And so in this point, we have work equals gravitational energy plus kinetic energy. Okay, so now you've got a visual definition of work, what work is, and it's so much more meaningful for our students. The second nuance for energy bar charts is that you choose where the 0 point is. So before we said that B was the 0 point for gravitational potential energy. So when it got to B, it had no gravitational potential energy. But let's imagine that Tiger's on a small hill. Okay, so B is no longer the 0 point. And at the bottom of the hill, sea level is our 0 point. So when the ball's up at this highest point, it's actually going to have, I'm going to say, 7 bars of energy. And when it gets to its lowest point, B, it doesn't have 0 because it's on a hill, it has 2 bars of energy. And you can see this is still balanced, right? 1, 2, 3, 4, 5, 6, 7 bars of energy become 1, 2, 3, 4, 5, 6, 7 bars of energy. So gravitational potential energy, it doesn't matter where you define the 0 point. You could have made A the 0 point and dealt with negative energies, as long as it's still consistent. This is a really good way to extend your students and get them to come up with some funky ideas of where gravitational potential energy is, but still show that your system is consistent with conservation of energy. So what's going to happen in the next video, I am going to go and give you a bunch of examples and where you can go to find more online and some online activities as well, and I'll just quickly go through 10-15 examples like that you can just use quickly in your classroom as part of year 11 or year 12 or year 13 conservation of energy problems using energy bar charts. I hope that's been helpful.